Hello Calc 3, welcome back to another video. This is the last video scheduled for the first week of class. The plan is to cover section 13.2, which is on integrals of vector equations and then projectile motion. So last section, in section 13.1, we developed the notion of a derivative for vector valued functions. And in this section, the plan is to develop the integral for vector valued functions. So let's start off with a definition. Like you might expect, if we have a vector valued function, big R of t, then big R of t is an antiderivative of little r of t if the derivative of big R of t with respect to t is equal to little r of t. So this is the same as the definition for an antiderivative that we had when we studied scalar functions in Calc 1 and 2. And secondly, if big R is an antiderivative of little r, it can be shown that every antiderivative of little r is of the form big R of t plus c, where c is a constant vector. Again, this is identical to a fact that we learned about scalar functions, where if we had some antiderivative typically denoted big F of x, then every antiderivative was of the form big F of x plus c. So this leads into our first big definition here. The indefinite integral of a vector valued function r with respect to t is defined to be the set of all antiderivatives of r, which is denoted by the integral of r of t dt, and also note that the integral of r of t dt is equal to big R of t plus c, where c is any constant and big R of t is any arbitrary antiderivative of little r that we choose. And here's another definition, this time the definite integral. So this was the indefinite integral, now down to the definite integral. If we have a vector valued function r, and we've written the component functions out, so we have f of t, g of t, and h of t as component functions here. And if all of those component functions are integrable over the interval from a to b, then so is the vector valued function r, and the definite integral of r from a to b is defined to be, well, first off, we're going to write it exactly how you would expect. So it's going to be the integral from a to b of r of t dt, and to calculate that definite integral, we're going to take the definite integral of the component functions. So we take the definite integral of f of t, the definite integral of g of t, and the definite integral of h of t, all from a to b, and those are going to give us our components of the integral of r of t. So just like the derivative in the previous section, to integrate a vector valued function, all we have to do is integrate each of the component functions. So let's move into an example here. We're going to use the same vector that we used in the last video in section 13.1, so we can let r equal cosine ti plus sine tj plus tk, and we want to find the definite integral from 0 to pi of our vector function r of t dt. So to find the integral from 0 to pi of r of t dt, we're going to find the integral of all of the component functions that are defining r of t. So for the I component, we end up with the integral from 0 to pi of cosine of t dt. For the j component, we have the integral from 0 to pi of sine of t dt. And for the k component, we have the integral from 0 to pi of t dt. Now the integral of cosine is sine, and we're going to evaluate at pi and 0 here to eventually get our I component. The integral of sine is negative cosine. The integral of t is 1/2 t squared. And now evaluating at pi and 0 in each of these expressions, we get that the I component is actually equal to 0, the j component is going to be equal to 2, and the k component is going to be equal to 1/2 pi squared. So we end up finding that the integral from 0 to pi of r of t dt, where r is a vector valued function, is equal to the vector 2j plus 1/2 pi squared k. So notice that the definite integral of r of t is a vector, not a scalar. When we take the definite integral of vector valued functions, we get vectors back as opposed to scalars. And finally, here's the fundamental theorem of calculus for continuous vector functions. So the definite integral from a to b of a vector valued function r of t dt is equal to big R of b minus big R of a, where big R is any antiderivative of little r. So this is the same as the fundamental theorem of calculus that we developed in, I think, chapter 5 towards the end of Calc 1 for scalar functions. So we have the same fundamental theorem of calculus for vector valued functions. So now we're going to move into an interesting application of the derivative and integral for vector valued functions that we've just defined in the past two sections. We're going to end up deriving the equations that describe projectile motion in 2 dimensions. So again, here we're talking about an object or a projectile that is moving in 2 directions. So it's not moving in 3-dimensional space, just 2-dimensional space, a horizontal and a vertical direction. And we're also going to assume that the only force acting on our projectile is the force of gravity, and that gravity is acting straight down towards the ground or towards the x-axis. So we're not going to account for things like drag or other miscellaneous forces that might act on objects while they're in the air. Also, the projectile is assumed to start at the origin, and it's going to be launched into the first quadrant. So you can see that in the first diagram here. Our object is starting at the origin right here, and it's going to be launched into the first object, so it's launched in this direction. So in the diagram, we have the vector v0 denoting our initial velocity vector. The angle alpha is the angle at which our projectile is being launched from the origin, and the vector A represents the force of gravity that is acting downwards on our projectile. So the first thing to notice, and you can see this from looking at the first diagram on the right, we have a right triangle here, and we can use that and some trig to figure out how to write our initial velocity vector in component form using other information that's given to us. So the I component for our initial velocity vector ends up being the magnitude of the velocity, or the speed, the initial speed of the projectile, multiplied by cosine of alpha, where again alpha is the launch angle of the projectile, and the j component is given by the magnitude of our initial velocity times sine of alpha. Again, we are assuming that the initial position of our projectile is going to be the origin. So another way to write that is r0 is equal to 0, or the position vector at time equals 0 is equal to 0. And the force acting on the projectile, this is just applying Newton's second law here. So the force acting on our projectile is going to equal the mass of our projectile times the acceleration of our projectile. So let's use this fact to get the ball rolling and see if we can figure out an equation describing the position of our projectile, just from these few facts that we know. So the only force acting on the projectile is gravity, which is something that we assumed. We're not going to account for drag or other kinds of forces. So because that is the case, Newton's second law tells us that the mass of our projectile times the acceleration of our projectile, which is the second derivative of the position function of our projectile, is going to equal negative mg in the j direction. So that's going down. And that's because the only force acting on our projectile is gravity. And of course we can divide both sides of this equation by m, and we end up finding that the acceleration of our projectile is equal to minus g in the j direction. So I haven't said it yet, but g is just the gravitational constant, so we can treat it as a constant for the rest of our calculations here. The important thing to take away from this little discussion here is that the acceleration function of our projectile is constant, and it's equal to negative g in the j direction. So it's going directly down parallel to the y-axis. Ultimately, our goal is to find the position function for our projectile, or r of t, and to do that we're going to have to solve a bunch of initial value problems here. So we have a couple of initial conditions that are given to us. We know that the projectile starts at the origin, so the position function, when we plug in t equals 0, should give us 0. And we also know the initial velocity, which is given in terms of the speed that we send the projectile off at and the launch angle alpha. So those are the two initial conditions that are given to us. Let's see if we can figure out the position function r. So first off, we want to find the indefinite integral of the acceleration function, or the second derivative of r with respect to t. And we just said above that the acceleration function is equal to negative g in the j direction. So if we want to take the indefinite integral of the acceleration function, we take the indefinite integral of negative g dt, and that's going to be the j component of the indefinite integral. And then of course we have to add a constant vector at the end, and we'll solve for that constant vector using our initial condition given to us. So we find that the indefinite integral of the acceleration function is negative g times t in the j direction plus some constant c, some constant vector. Now we want to solve for that constant vector. So we're given that at t equals 0, our velocity function should be equal to the speed, or the initial speed that's given to the projectile times cosine alpha in the I direction, plus the initial speed times sine alpha in the j direction. And using this fact to solve for c, we end up finding that c is actually equal to that initial velocity vector. So c is going to be equal to v naught. And once we know that, we can just write down the entire function for velocity in terms of t. So we end up with negative gt times the vector j plus the initial speed times cosine alpha I plus the initial speed times sine alpha j. And now we can make it look a little bit nicer by combining some terms. And we get the magnitude of v naught times cosine alpha in the I direction plus the magnitude of v naught sine alpha minus gt in the j direction. So this is going to be our vector valued function giving us the velocity of our projectile with respect to t. And now we want to integrate again to find our position function. So we know that the position function is going to be an antiderivative of our velocity function. So we'll find the antiderivative of our velocity function first, or the indefinite integral of our velocity function. And to do that, we integrate component-wise. So we find that the I component for our velocity function was a constant. It was just the magnitude of v naught times cosine alpha. So when we take the integral, we get the magnitude of v naught times t times cosine alpha, and that'll be the I component of our position function. And now for the j component, this magnitude of v naught sine alpha again is a constant, So we get the magnitude of v naught times t times sine alpha. And then we just have left the indefinite integral of minus g times t. That'll give us a minus 1/2 times g times t squared. And that'll be in the j direction. And now, of course, we need to add our constant vector c at the end, and we're going to solve for that constant vector using our initial condition. So when t equals 0, we know that our position function needs to equal 0 because we assumed that our projectile was starting at the origin. And that fact ends up requiring c to equal 0. And because that is the case, now we can write down our final equation for the position function. So our position function r of t will equal, in the I direction, the magnitude of v naught times t times cosine alpha, and in the j direction, the magnitude of v naught times t times sine alpha minus 1/2 times g times t squared. So this looks a little bit complicated, but this will give us an equation that kind of describes comprehensively what the motion of our projectile will look like if we only have the force of gravity acting on the projectile, and if we're given information about the launch angle and how quickly we're sending it off into the air. So let's just sum this up here. So when we have ideal projectile motion, which is just projectile motion where you're starting at the origin and the only force acting on your object is gravity, then the position function for our object is given by r of t is equal to the magnitude of v naught times cosine alpha t in the I direction, and then the magnitude of v naught sine alpha t minus 1/2 g t squared, all in the j direction. And if we want to, instead of representing that as a vector valued equation, we could instead just represent it as parametric equations. So we can read right off of this vector valued function here that x is going to be equal to the magnitude of v naught times cosine alpha t, and y is going to equal v naught times sine alpha t minus 1/2 g t squared for t greater than or equal to 0, probably until the projectile hits the ground, although I don't think that's specified in the book, but I think it's safe to assume this only holds for t until the projectile hits the ground, though of course if there is no ground, then the equations would continue to hold for as big t as you would like. So let's apply this to an example. Let's assume that a projectile is fired from the origin and its initial speed is 500 meters per second and its launch angle is 60 degrees. The question is, where will the projectile be 10 seconds later? Well, we just developed parametric equations for the curve that describes projectile motion, so we can use those parametric equations to get coordinates for our projectile. So x is going to equal the magnitude of v naught, which is the same as the initial speed, times cosine of our launch angle times the time we're interested in, which gives us 500 times the cosine of 60 degrees times 10. And y, our y coordinate for the projectile, is going to be equal to 500 times the sine of 60 degrees times 10 minus 1/2 g times 10 squared, where again, g is just the gravitational constant, should be somewhere around 9.8 meters per second squared. And now we can just plug all of these different numbers into the calculator and calculate. We get that x is equal to 2,500 meters and y is right about 3,840 meters. So at time equals 10, those give the coordinates for our projectile. The coordinates would be 2,500, 3,840 in meters. Now let's move on to the last piece of information for projectile motion, at least in this section. So we're going to talk about height, flight time, and range of our projectile. So when we have ideal projectile motion, which again means that the only force acting on our projectile is gravity, and the projectile is starting from the origin, then we can develop these equations that give us various information about the projectile. So the first piece of information is the maximum height of our projectile as it's traveling its curve. We find that the maximum height is equal to the initial speed times sine alpha squared, all over 2 times the gravitational constant. The flight time is equal to 2 times the initial speed times sine alpha over g. And the range, which is how far the projectile is going to go before it hits the ground, is given by the initial speed squared over g times sine of 2 alpha. So all of these formulas can be proved using the information that we already have to describe projectile motion. I am only going to give a proof for the first formula, the max height, and the other proofs are going to be left to you if you'd like to prove them, or I'm sure you could find them online if you looked as well. But let's just go through the proof for the formula for the maximum height of our projectile. So the first thing to notice is that the projectile is going to reach its highest height, or its maximum height, when the j component of the velocity vector is equal to 0. So if we ignore the x component of the projectile motion, and we're only concerned about the y component, or the j component of our projectile motion, then the projectile motion is kind of going to look like an object that just goes straight up into the air, and it hits some point and then comes straight back down. So I kind of have to draw the arrows next to each other, but just think about an object going straight up in the air and then coming straight back down, and that's going to describe the motion of our projectile in the j direction, or in the y direction. And if that's the case, then I think we can agree that the projectile reaches its highest height when the j component of the velocity vector is equal to 0. Because when the object hits its peak, we're going to have a change in the direction of the velocity. So originally it's positive, it's going up, and then it's going to hit a point where it becomes 0 and comes back down, and the point at which the velocity is 0 is going to be maximum, because after that the velocity will be negative, going downwards back towards the ground. So if that is the case, then let's just look at the j component of our velocity vector. So if we go back up to when we were deriving our position vector here, we have an expression for the velocity vector. So v of t is equal to this here. And again, we're only worried about the j component. We want to find when the j component of the velocity vector is equal to 0. So notice that the j component is equal to the initial speed times sine of alpha minus gt, which is exactly what I have written here. So we're looking for when that is equal to 0. And doing a little bit of algebra, we find that that happens at time equal to initial speed times sine alpha divided by g. So that is going to be the time when our projectile hits its maximum height. And now that we have the time that that the projectile hits the maximum height, we want to find what the maximum height actually is. And to do that, we're going to find the j component of our position vector r when we plug in the time that we just found. So we want the j component of r when we evaluate r at the initial speed times sine alpha divided by g. And the j component of r is given to us because we just found it. That is going to be the second half of our equation here. So this is our j component. We want to see what happens to that j component when we plug in the time that we found. And when we do that, we find the initial speed times sine alpha times the initial speed times sine alpha divided by g. This is just substituting for t here. And then we substitute for t over here as well. And again, doing a little bit of algebra from here to here, and then from there to there, we end up finding that the maximum height of our projectile is equal to the initial speed times sine alpha, where all of that is squared, divided by 2 times the gravitational constant. And fortunately, that lines up with the equation right here for maximum height, so we can be confident that the derivation of that formula is correct. And again, the other proofs I'm not going to go through here. If you want to, you can find them online or try and do them yourselves. I think that it's going to be somewhat of a similar process. So that is the end of the material for section 13.2. Not too long of a section, and we will be covering sections 13.3 and 13.4 soon, so keep a lookout for those.